Okay, thank you all for attending. My name is Peter Barrett, and this is the CivilFEM Geotechnical webinar. It's the second webinar in a series that we're providing on the CivilFEM software. In case you missed last month's overview of CivilFEM, you can access through our web and download it. And we will also tape this presentation for further viewing. Interesting, when I was putting this thing together, I found a slide that kind of gives an interesting aspect of where we've come in terms of finite element analysis, and in particular this application was in the geotechnical area, where not too long ago, 1995, our model sizes were in the order of 1,000 elements, and now we're solving models that are 1 million elements. And having that capability allows us to solve some very interesting and challenging problems, and I think you'll find that the CivilFEM program and the geotechnical capabilities give you the ability to solve some very interesting, complex problems in this arena. So for those that aren't familiar, what is CivilFEM? It's an integrated pre-solution post-processor add-on to ANSYS. It was developed or is developed by the Spanish distributor of ANSYS, INGECIBER. They're a long-time ANSYS distributor for 25, 30 years. In fact, their origins come from Miguel Moreno, who actually worked for Westinghouse at the same time John Swanson was there. So they have a long history of dealing with ANSYS. What they've done is put together an adaptation to ANSYS where we leverage the ANSYS capabilities but give us the option to solve complex problems. In this case, we'll talk about geotechnical applications. So INGECIBER, the other thing is they're fully QA. They have ISO 9000 certification. They're working with a number of companies in the nuclear industry as well, so they've gone through and been audited by companies like Westinghouse. The customer base is worldwide. There's a number of customers throughout Europe, Asia, U.S., South America. I'm sure everybody's familiar with ANSYS, but just to give you a global overview, ANSYS is the world's largest simulation community. With recent acquisitions over the last few years of Fluent and Ansoft, we now provide a full suite of software products to capture any kind of analytical simulations. And more work has been put in the arena of coupled field simulations over the last few years, in particular the coupled fluid structure interaction for solving both fluid and structural problems, and we've done that kind of simulations using ANSYS CFX and the ANSYS mechanical product. Current customers for CAE Associates, Arriva, AECOM, Parsons, Leslie Robinson, Westinghouse is also a big user of ANSYS CivilFEM, just to name a few. So how does ANSYS and CivilFEM, how are they integrated? The CivilFEM is a series of GUI options, user-defined routines that are fully integrated into the ANSYS graphical user interface. In addition, there are items such as material laws and post-processing routines where ANSYS and CivilFEM are integrated, where CivilFEM actually will create its own database and results file that are used together with the ANSYS results to provide specific post-processing for the civil engineering industry. For example, code checking applications, looking at a whole series of loading operations, loading conditions, finding the worst case scenario, looking at worst case combinations, and in a variety of other different applications. CivilFEM is also integrated on the front end of ANSYS, where there is automation and pre-processing in terms of building models, not only for the mechanics area and geotechnical, but also for bridges, pre-stressed building, concrete buildings, for example, a series of designs of various different AISC and ACI and European sections as well. CivilFEM is command-driven, similar to ANSYS. So you see in the lower corner of the screen that there is a ~CF get command. All of the CivilFEM capabilities are driven by commands similar to ANSYS, so they can be fully integrated into a solution sequence. In terms of documentation, the CivilFEM has online help similar to ANSYS. You can scroll between various different menus in the HTML environment. There also are examples manuals, both simple demonstration as well as more complicated models. These advanced workshops have the full input streams that produce them provided, and thus you can take them, edit them, you can actually modify them and customize them for your particular application. There are also training classes that we teach in our office, both general and specific mentoring type applications that we can provide as well. CivilFEM has a number of distributors worldwide, and then there's a little illustration of our office in Connecticut. You can see there's a big concentration in Europe where there are a number of customers of CivilFEM due to the origins of Spain, as well as offices on all the different continents. Just a little background on CAE Associates. For those who aren't familiar, we're one of the first ANSYS channel partners. We've been a consulting engineering company since 1981. We've been an ANSYS channel partner since '85. And we've been interfacing with INGECIBER for many years, and in the last few years now, we're actually a retail vendor of CivilFEM. As a CivilFEM ANSYS partner, we are also a consulting company, so we can perform simulations, develop models, modify models. We can also do training. In fact, we probably teach more ANSYS training classes than anybody worldwide. We're the exclusive ANSYS trainer for companies like General Electric and Pratt & Whitney and other industries, as well as we do a number of different applications. We did customized classes for SGH up in Boston recently. So we've done the application of various training programs for a variety of customers throughout the U.S. On the consulting end, we were involved in the investigation of the World Trade Center collapse. We've done analysis of replacements for steam generators, pre-stressed concrete pipe simulations, buried pipes, concrete dam simulations to meet FERC and U.S. Corps of Engineers licensing, just to name a few in the civil application area. Technical staff at CAE Associates consists of people from a variety of different backgrounds and universities. ANSYS strengths. ANSYS, of course, from the structural perspective, can solve a full suite of nonlinear analysis, various contact problems, plasticity, creep, large deflection. And the nice thing about the solution capabilities is any feature of ANSYS can be integrated and combined with the CivilFEM features as well. So because they're both command-driven, they can be integrated at any point in time. Your model can be run in ANSYS, and then some post-processing done with the CivilFEM add-on features. Your model can be developed in the CivilFEM front-end to ANSYS with a mixture of generating the geometry in ANSYS, generating the materials in CivilFEM, etc. So the CivilFEM takes advantage of all the ANSYS capabilities and supplements that for things that may not be as intuitive or easy to use in the geotechnical arena, which we'll describe in the next 40 minutes or so. One of the interesting areas coming out in the next release of ANSYS, due out in about a month, is a new suite of elements that can analyze a coupled field solution of a combined mechanical solution with coupled with pore pressure. So each of these elements have not only the translational degrees of freedom for displacement, but also a extra degree of freedom for pore pressure. So you can do a fully coupled integrated analysis with this new element type. So what are CivilFEM strengths? CivilFEM is an adjunct to ANSYS, but it has the ability for one button click to create up to 4,000 different section IDs. So if you have a certain I-beam, a L section from a specific code, you can define that section and use that. It has a full suite of material models. That's probably one of the biggest strengths from the perspective of the geotechnical applications, is there are both soft soils, hard soils, different rock material laws, cohesionless. A full suite of materials are available to be accessed in the CivilFEM material library. As I mentioned, the different modules include the nonlinear bridge simulation, pre-stressed concrete, and nuclear applications, but for this webinar, we're going to concentrate on the CivilFEM geotechnical module. So, when you're running CivilFEM in conjunction with ANSYS, you have the option to either activate or deactivate any of the CivilFEM modules. So you can have all of CivilFEM integrated directly with your ANSYS particular analysis you're running, or you can deactivate the CivilFEM add-on to ANSYS. And if you notice on the left-hand side, the CivilFEM menus simply fall below the ANSYS menus in the traditional ANSYS main menu. So we have capabilities for CivilFEM pre-processing, solution, and post-processing, and then there's a series of more detailed specifications to certain areas, for instance, in the bridge design or pre-stressed concrete. An overview of the geotechnical capabilities in CivilFEM includes a full suite library of various material laws for soils and rocks, the ability to define a layered terrain, so you can take these different material models that you set up, specify different layers of each of these to set up your terrain. Then once you've got this terrain set up, then you can run a series of different types of simulations. Retaining wall design, where you can do the excavation behind the retaining wall, and at any point during that simulation, calculate, for instance, do a design evaluation of maybe the concrete wall or piling. You can do seepage analysis. So once you've got your soil set up, you can figure out the flow through the, maybe it's a dam or a different foundation setup. Slope stability. We can look at various empirical type slope stability evaluations, or we can do a finite element-based slope stability evaluation. In the area of tunneling, CivilFEM leverages the traditional ANSYS birth and death type capability to allow you to simulate the excavation process in 2D and 3D, and there is a wizard available to automate this process. We can calculate automatically the pressures, the earth pressures that we would see in an underground tank, for example. We can specify an initial stress state to simulate the terrain without inducing any strain. And then there's a series of modules for doing foundation pile design. This includes both the regular full-scale piles and micro piles. So if we start with the geotechnical material libraries, the material libraries fall into, for soils, fall into two areas for the geotechnical area, for soils and for rock. And if we look at the selection process, what you would do, this is just some snapshots from the GUI. When you specify soil, you can see in the details there's a dozen different operations, from sand to gravel to silt to clay to peat. And for each of those entities, there are predefined set of material laws available to be accessed and used in any one of the geotechnical applications within the CivilFEM suite. If we instead select the rock type material, you can see that for the rock type material, now it's broken into sedimentary, igneous, metamorphic. So we've specified different rock types as well, and for each of those rock types, there are subsets. So we can get down to the point of selecting, for instance, a certain limestone and define the associated material properties, which are automatically built into the CivilFEM suite, so they're directly accessible immediately for any ANSYS CivilFEM simulation. And for each of these different types of analysis, so if we're doing, for instance, in this case, a pile simulation, if we click on the wizard at the bottom of the soil material input window, it gives us some detailed information about what data is relevant. For this cohesionless soil, what kind of input? We can input information from our standard penetration test, for instance, the specific weight and moisture content, these kinds of things. So the input is relevant to the industry and then translated as appropriate into things like modulus elasticity, et cetera, for the actual simulation calculation. The material setup in CivilFEM can be broken into a series of 7 different groups: general properties, structural analysis, structural weight, things like grain size, correlations, and CivilFEM also has an interface to FLAC 3D in terms of a pre- and post-processor for that other soil mechanics piece of software that allows you to do some Laplacian type calculations. So I'm not going to go through the details of each of these, but just on your screen you'll see a couple different options. Here's the structural analysis simulations, and you can see that some of the areas the modulus is grayed out because it comes from some other internal calculation. Specific weights, densities, porosity, water canter, some of these items are things you can fill in, or they're calculated from one of the other fields. So other areas we can input information in, for example, here the standard penetration test properties would be something, or more Coulomb. We can put in a cohesion or internal friction angle. So those are just some of the inputs into the CivilFEM material properties. Now these are predefined for all the soils defined in the library, but you can also modify these and create your own library of materials. If we're looking at a granular type material, grand size parameters for soils. If we're looking at rock, then we can look at the Hoek and Brown parameters, for example. Another thing that CivilFEM provides either automatically or allows the user to define is what it calls correlations. And probably the most common one in the geotechnical area would be a correlation between the standard penetration test and maybe the modulus of elasticity. So you can specify a correlation so that the properties that CivilFEM will use will be appropriately scaled, modified, based on some equation that you define. You can use the default correlations provided in the program, or you can build your own series of correlations. So user-defined correlations can be set up by writing equations, and you can create comments, etc., to define these correlations. Some examples of some other material laws, or some of the material laws built in to the ANSYS CivilFEM product, is the CAP Drucker-Prager plasticity law for soils. More Coulomb failure criterion can be accessed. This is also just an example pulled out of one of the help pages, so you can see that the online help provides not only the demonstration of how to apply the capability, but also the theory and equations behind the program functions of CivilFEM. So the second step in performing any kind of simulation with CivilFEM is to define the layered terrain. So once you've defined and selected your material properties, now you can take those material properties and apply them to some kind of layered terrain. CivilFEM will take this data and make the appropriate calculations to be used in any of the other types of geotechnical calculation schemes, such as it can take, if we're doing a retaining wall simulation, it takes this data and creates the equivalent elements that we can use in, for instance, a 2D simulation of the material both behind and the material being excavated from the retaining wall. So layered terrains, they don't have to line up exclusively with the finite elements. The layered terrain is set up separately. CivilFEM will automatically apply the appropriate material properties across to the finite elements where applicable to provide the appropriate material response. So, next step is, once you've defined the materials or selected the materials from the library, defined your terrain based on those materials, now we can take and run a series of different solutions or setup for various analysis, taking that data into account. One of the direct applications is developing earth pressures, developing what's called a ballast module, basically a soil foundation stiffness, which is a function of the underground soil definition, but in the analytical model can simply be an elastic foundation if you don't desire to model the earth in detail. If we have a buried structure, for example, and we're looking at using, we can use the automated earth pressure formulation in CivilFEM. So CivilFEM will figure out, based on the cumulative layers of soil, their density, the pressure at rest, active pressure, passive pressure, and it can apply these to the full suite of element types available in ANSYS, whether they be beam, shell, solids, or surface effect elements. And the earth pressures not only can provide you with the vertical, but also the horizontal, based on the equations that you might find in most geotechnical handbooks, where they sum up the definition of the layers and the densities and come up with the cohesion levels and calculate the equivalent lateral load to be applied to the model. If we're looking for an elastic foundation type simulation, again, we can set up our full series of the underlying soil layers, and then CivilFEM will come up and will calculate the elastic foundation stiffness, and we can then apply that stiffness to our simulation. So the foundation results is not necessarily going to be uniform, so we can have a non-uniform foundation stiffness that we can use to simulate to look at relative settlement, for example, in our structure. Moving on to retaining walls. The retaining wall calculation is automated in CivilFEM. They can be 1D, 2D, 3D type simulations. The simulation will step through the construction sequence. CivilFEM takes advantage of all the nonlinear analysis capabilities in ANSYS. So it can do automated birth and death. It can do the nonlinear force deflection response and calculate the appropriate loads, stresses, forces in the members, in the wall itself, in individual beams. You can pretty much integrate any ANSYS feature into any of these different processes. If you use the wizard for 2D sheet piles, there's an automatic capability where you can simply specify the, once you define your materials and terrain, you can specify the excavation process. You can include, if you want, a support beam across the excavation, and you can walk through the step visually, seeing the material being excavated, and at any point in time you can look at results, deformations, member forces and moments, stresses, etc. Calculation can be 2D. You can also do 3D simulations. These integrated into, or the automated process does one or two walls. You can see on the left there's a graph of some results, maybe like the bending moment diagram along that face, actually, or a safety utilization factor, I think, is the utilization of the bending moment. The automated process will go and create a series of links to represent both the passive and active earth pressures on our structure. These are nonlinear material laws, which can carry out the nonlinear elastic behavior of the particular spring representing the retaining wall and the appropriate connections. There is general GUI setup for setting up multiple walls. You can have multiple different terrains that are defined. You can automate the generation of these different sequences. You can have different types of anchorages, anchorages that are fixed, anchorages that will move when the wall moves, so you can either have them update or not update. So, details on retaining walls. The next subject is seepage analysis. So in the area of seepage analysis, the CivilFEM product will calculate the hydraulic head and pore water pressures. You can calculate flow based on Darcy's law. Again, you would set up your model with the appropriate materials from the material library. You set up your terrains. You set up your mesh, your finite element mesh, and set up particular boundary conditions. And CivilFEM will actually calculate from that using a thermal analogy the seepage through that sector. So it doesn't require you to have a thermal analysis capability. You can take just the structural elements. Internally, the CivilFEM add-on subroutines give you the ability to calculate the hydraulic head where it makes an analogy and takes the UX displacement degree of freedom and uses that as the degree of freedom used for the hydraulic head to calculate the seepage. And it's going to be applied to both 2D and 3D ANSYS elements. So you use the standard ANSYS elements, are integrated by CivilFEM and applied, and from that we can pull off the seepage calculation. So we can calculate the particular seepage or the seepage surface. And once we've calculated this saturation line or seepage surface, we can use this as the front end into our slope stability calculations. The slope stability calculations available in CivilFEM are both classical methods as well as finite element based methods. The classic methods include Bishop, Jambu. These can include both the circular reference or the polygon type shaped, or you can use the finite element method, and you compare and contrast any of these. Each of these calculation capabilities are available in ANSYS by means of, well, for instance, the finite element method safety factor simulation. We can look at a series of different slices, take our pore water pressure, and come up with the equivalent slope stability safety factors. The safety factors can be calculated for each of the different methods, whether the finite element or the, for instance, Bishop's method. And the solution, once it's completed, from the post-processing perspective, we can look at the results in a graphical wizard type format. So the slope stability calculation gives us a safety factor map as well as a max safety factor. For the slope stability calculation, we can change the various different criterions and compare and contrast using the slope stability evaluation technique. Moving on to tunneling, another area of feature functionality in the CivilFEM geotechnical capability. There is a wizard available for both 2D and 3D tunnel simulations. The tunneling capability in CivilFEM takes advantage of some of the nonlinear material laws as well as the birth and death features of ANSYS, and it automates it. In fact, all of the material libraries in CivilFEM can be set up with a activation and deactivation times. And CivilFEM uses a thermal analogy. It takes advantage of the temperature-dependent material properties in ANSYS to give you the ability to model a construction sequence, or in this case, the tunneling or the removal of material. And during that process, evaluate the forces, displacements, stresses on members throughout the tunneling operation. So nonlinear sequence is available. We can pull off detail forces and moments, stresses. We can use this in conjunction with the initial stress definition, with some of the advanced material laws, and again, the process of evaluating, including the construction process of the tunnel, is provided with the CivilFEM and with the CivilFEM tunneling wizard. Just an example, a couple slides of the tunneling wizard where you can specify the area of excavation. You can also add in, if there's an internal lining or beams being added, you can have those be constructed using the birth and death features as well. So any columns or support structure, you can evaluate them when they're actually implemented and how they interact with the additional tunneling that gets simulated. And you can have a series of construction phases, real no limit in terms of the number of construction phases. Everything is sequential. Since it's a sequential analysis, the results from the next step are a function of the previous step. A feature that CivilFEM has added on the computational end is the ability to define the Hoek and Brown material failure criterion for rock. It allows us to look at the rock mass rating and select a particular failure model, whether we use the original or modified response. And the CivilFEM uses its capability in conjunction with ANSYS to create an iterative loop for solving using the nonlinear Drucker-Prager material law. We can look at different confinements. The setup for CivilFEM is based on parameters typically used to define the Hoek and Brown failure, such as the compressive resistance of the rock. And the iterative solution process works through taking the Hoek and Brown coefficients, coming up with more Coulomb values, plugging those into Drucker-Prager, solving the analysis, extracting the principal stresses, plugging those values back into the criterion, and so on. And this is done in an automated sequence There's GUI picks to do some of the individual parameters. But basically, most of the time, CivilFEM you can run from a scripting or in a batch mode process where you can go through and set up a input deck of commands that address defining materials, defining our terrain, defining the various different applications we're looking at, retaining walls, etc., and post-processing. And once these automated input scripts are created, then you can do a series of what-if scenarios. You can even take advantage of ANSYS's design optimization routines because all of the CivilFEM capabilities are totally integrated into ANSYS. So you could use design optimization to optimize the size of your retaining wall, the number of members that you're going to use in terms of your piles, etc. Terrain initial stress is another feature of CivilFEM where you can develop the equivalent stress state in the actual soil in a strain-free condition. It takes advantage of the initial stress capabilities in ANSYS. You can create both a vertical and horizontal stress state in the actual soil based on the initial terrain. This creates a external file where the only really definition you need to specify is the direction of gravity. Foundation piles, another area of a wizard developed in CivilFEM to simplify the process of designing piles. The pile cap wizard is an automatic generation, both rectangular, polygon, circular pile groups. These piles can be driven piles, excavated piles, or micro piles. We can look at the amount of, evaluate the amount of reinforcement required in the pile. For the polygon or circular, you can bring up the wizard that will walk you through specifying a nominal number of dimensions and numbers of piles, diameters. So in the nature of a few button clicks and predefined material and terrain, you can do very detailed pile simulation in CivilFEM. Similar capability in terms of defining the rectangular pile. CivilFEM will break the soil response that it creates into both cohesive and cohesionless soils. And it takes this diagram, which is the internal friction angle versus cohesion, and the limit can be changed, but the limit right now is the 25 on the friction angle and 20 on the cohesion. That's kilopascals in this particular example here. So if it's in the pink area, it's going to be defined as a cohesionless soil. If it's in the green area, it's going to be defined as a cohesive soil. From this data from the cohesive soils, the skin friction is calculated where we get the resistance, force versus deflection response. We get this skin friction or drag based on the values of the material. It pulls data from various charts that are available within CivilFEM, although the values can be overridden, and you can specify your own constraints as well. We have both a frictional type resistance as well as point resistance. And again, the point resistance capabilities can be modified. The default values are predefined. And this applies not only to the cohesion, but also the cohesionless soils. The pile capacity is a function, of course, of the depth of the pile, and that's taken into account directly in the CivilFEM module in terms of defining the resistance. The underlying soil is also taken into account in the point effect correction, so we can look at the effect of the underlying active zone as well as the security zone below the pile itself. CivilFEM will also take into account the fact that if there are a number of piles that are grouped closely together, and it takes into account the grouping effect of the piles on and their response on the force versus settlement or force versus deflection. It also looks at the design strength in terms of the structural capacity versus pile diameter, both for a service type load or earthquake type response. And all this data is then taken and developed and compiled into a series of equivalent springs, both horizontal, vertical, and point type springs that allow for a very rapid representation of a pile response. From an external perspective, one can apply loads, forces, and moments on the column itself, pressures on the slab, self-weight, any seismic type evaluation. We can look at, in terms of reinforcement definition, either rigid or flexible caps. And the wizard has a series of tabs where you define the geometry of the particular pile set, the loads that are applied, forces and moments on the top section, the type of reinforcement we're going to use for this particular group of piles, and the soil terrain. This is a soil terrain that can be imported from the terrain definition or specified here in the pile wizard. Configurations in terms of the density of the mesh parameters can also be defined, convergence criterion for the solution, and then post-processing we can look at the various options in terms of the pile strength, etc. That's just an example of displacements of a series of piles and representing the finite elements. So that concludes a quick overview of the geotechnical capabilities of ANSYS CivilFEM. Our next presentation will be May 13th on the nonlinear pre-stressed bridge capabilities. We'll also be attending the bridge conference in Pittsburgh coming up the middle of June, and the nuclear applications seminar or webinar is scheduled for July.